So in the previous video, we talked about a couple of different terms, enthalpy and entropy, which are both used in thermodynamic problems. In this video, I want to talk about a couple of different enthalpies. All right. The first of these is what's called the enthalpy of formation, and this is the enthalpy change that you get when 1 mole of a compound is formed from its elements in their elemental forms at standard temperature and pressure. All right. So one thing I didn't write down here, but you should go ahead and include in your notes, is what standard temperature and pressure would be considered to be 298 Kelvin and 100 kilopascals, or 100 kPa. All right. So if you were to say what is the standard enthalpy of formation of ethane, all right, what that would involve is saying, okay, well, let's take a look at the elements that go into making this up. All right, we've got carbon and we've got hydrogen. All right, so if we took carbon in its elemental form, its formula would be C. Actually, carbon comes in a couple different forms. I believe the form that's generally used for these equations would be graphite, and the formula for that would just be plain old C. All right, but the elemental form, the form that pure hydrogen comes would be available to us as would be H2. All right, remember hydrogen is one of those Brinkelhoff elements, so it would come as essentially a pair of hydrogens which are bonded together. All right, so what the enthalpy of formation would be is if carbon were to react with H2 to make the compound that we're interested in. All right, C2H6. All right, so to balance that, we would put a 2 here and a 3 here, and we would get our desired compound. Okay, and one thing I want to point out about this balanced reaction, even though you should know how to balance reactions, it's not always going to be in the form of the balanced reaction that you're used to. All right, the reason that it works for this particular reaction right here is that notice that the definition is when 1 mole of a compound is formed. All right. Notice that when we balance this, it gives us exactly 1 as a coefficient for the compound that we're interested in here. We're trying to form 1 mole of this thing right here. So this would be appropriate for this for reporting its standard enthalpy of formation. All right. And the way that you would you represent that is with this delta HF with this little superscript right here, and that's the superscript that means at standard conditions, which means the 298 Kelvin and the 100 kilopascals. All right. So FYI, all of these, there's a lot of these bits of data that are in your data booklet. This is in table 12, and you'll notice that for all these compounds right here, one of the quantities that they give you is that standard enthalpy of formation. All right, and notice it's in kilojoules per mole. All right, and that's why, since it says per mole, that's why when you have your balanced equation, this needs to be 1 right here. Okay, so another example, ethanol. All right, if we take that, this has only got carbon, hydrogen, and oxygen. All right, so first of all, ask yourself how does carbon come to us in its elemental form? It would just be plain old C. Hydrogen comes as H2, and oxygen comes as O2. All right, and we're trying to make ethanol, whose formula is this right here. All right, so if we go ahead and balance that, this is what we would get as a balanced equation. All right, so there's a problem with using this as the equation with which to represent the standard enthalpy of formation, and that's because, remember, it's when 1 mole of a compound is formed. All right, this would show when 2 moles of that compound is formed. All right, so whenever you have a situation like this, you want to go ahead and do something which we're not used to seeing in balanced equations, which is we're going to end up representing some of our reactants and products as fractions. All right, so to get this as 1, we're going to go ahead and divide everything by 2. All right, so when we divide both sides by 2, notice the 2 becomes a 1 here, and everything else gets divided. But notice that we end up getting this half. in front of something. And again, we don't normally do that with balanced equations, but whenever you're reporting these standard enthalpies of formation, sometimes you're going to get things that have these fractions, all right? And that's for the sake of making this, showing this so that this is per 1 mole of that compound that gets formed, all right? And unless we do that, we can't represent this as per 1 mole, all right? So, moving on. Standard enthalpy of combustion is the enthalpy change, and in this case, since we're talking about combustion, enthalpy change is going to be the same thing as heat released, all right? If you say enthalpy change, it's going to be a negative value, but if you just report it as a positive value, that would be the same thing as the amount of heat that's released, all right? So it's going to be that per 1 mole of a substance when it's completely combusted in oxygen under standard conditions. All right. So if we wanted to do this for methane, all right. So essentially what we're doing is we're showing how much energy can get released whenever you burn something. All right. It's going to be different for methane versus methanol versus propane. So again, we have that same situation where we want to do this per 1 mole of the substance. So if we balance the combustion reaction of methane, you'll notice that when it's balanced, it's such that this is got a 1 in front of methane. All right, so that would be fine because it meets that requirement of the definition, per 1 mole of the substance which is being combusted. All right, so we can... So for all these enthalpies of combustion, we're going to find, you can find those in table 13 of your data booklet. And again, it's essentially just saying for every 1 mole of any of these materials that you burned with an excess of oxygen, how much, what would be the enthalpy change? And another way of saying that is how much heat would be given off when these things burned. All right, so that's where we would get this value right here for the reaction involving methane. All right, so let's say that we wanted to do this with methanol. All right, well again, starting from scratch, if you just write down the formula for methanol, say we're going to react it with oxygen, and it comes as O2 in the air. We always make carbon dioxide and water. Go ahead and balance this, and we end up getting these coefficients. All right, so this is a situation where we're going to have to manipulate that reaction just a little bit. You'll see in the next subject, which is Hess's law, why we sometimes need to do this. All right, so you'll notice, since we need to do this per 1 mole of the substance, well, this would show per 2 moles of methanol. All right, so we're going to do the same thing again. We're going to divide everything by whatever that coefficient is right there. So we divide that by 2. All right, and that's going to end up giving us 3/2 of an oxygen molecule. And I know that looks a little odd, but when you practice these Hess's law problems, it gets a lot simpler. So again, you will end up getting your standard enthalpy change of combustion. You do this just by looking it up off that data table in the data booklet that I just showed you. And that's it for that topic. And the last type of enthalpy that you're going to be responsible for knowing is what are called bond enthalpies. And this is a little bit abstract, because the types of reactions that we're going to be showing here are not types of reactions that are easy to do directly. All right. So essentially, what a bond enthalpy is, it's the energy required to break a type of chemical bond. All right, and these values are listed in table 11. Okay, this is table 11 of the data booklet. So what this would show you, all right, so this table right here would be for all single bonds. So if we wanted to break say for example, a carbon-fluorine single bond, all right, that would be 255 kilojoules per mole. All right, if we wanted to break a carbon-fluorine chemical single bond, that would be 492 kilojoules per mole. The reason that this is a little abstract is there is no direct chemical reaction that we can do, which would involve, taking a substance which was only carbon single bonded to a fluorine. All right. Hopefully you realize a carbon compounds are going to have four bonds to them, so we can't do this individually. But what this is essentially trying to say is, let's say that we had CF4. All right, and that is a compound that we could have. How much energy would be involved in breaking one of those bonds? All right, so again, in general, this is the way what that data table represents. If we had a bond, and we're going to say, let's break that. All right. So whenever you break chemical bonds, that requires that energy is put in to the system. All right. It would require energy to break this bond. All right. So if we take that and we break it apart, all right, that's what this reaction right here would show. Your delta H is going to be positive, meaning that energy is required in order for that to happen. And notice that's why all of these right here are represented as positive values. All right. Notice that this is all for single bonds. If you have any multiple bonds, a lot of those are listed down here individually, and you could use those as well. All right. But something else that you can do is, if we just take this reaction and we turn it the other way, we say, let's start with the individual atoms and we make the bond. All right. Well, when bonds are made, energy is released. All right. And therefore, the delta H would be negative. All right. So in a situation like this, all you have to do is, like, let's say how much energy is released when a carbon hydrogen single bond is made. All right. That would be 414. The enthalpy change would be negative 414, because you're just turning this around. Instead of saying how much energy would it take to break it, you're saying how much energy would be released if one of these made a bond with one of these. Okay, so a couple details about this. Again, I mentioned before, the type of bond matters. All right, so there's a difference between the amount of energy required to break a carbon-carbon single bond versus a carbon-carbon double bond. All right, and you can find both of those values in the booklet. Make sure that when you're doing these problems, you do pay attention to whether it's a double bond or single bond. All right. Another thing is that all of these values are average values for a type of bond. All right. So that's actually going to cause a little bit of a limitation in terms of how much accuracy you can get out of trying to solve problems using these. But here's an example of what they mean by why this is an average. All right. So take a look at this molecule right here. This is ethanol. And notice that there are two types of carbon-hydrogen bonds. There's the carbon-hydrogen bond right here, and there's a carbon-hydrogen bond right here. And the thing about this table right here is it just says this is the amount of energy required to break an average carbon-hydrogen bond. Well, the thing is, real carbon-hydrogen bonds aren't necessarily the same as an average carbon-hydrogen bond. So that 414 kilojoules per mole that they list in the data booklet isn't necessarily exactly the amount of energy for this one, nor is it exactly the amount of energy required to break this bond. All right. In fact, the amount of energy would probably be different between these because they have different neighbors. All right. If you look at the electron withdrawing groups, there's a polar bond attached to this guy right here. There aren't any polar bonds attached to this guy right here. So that's probably going to mean that these are going to take slightly different amounts of energy to break those. All right. But still, when we're doing these types of problems, we can use that value, but just realize that that value is for an average bond, and that it's for each individual bond, it's not necessarily the exact as the one that's reported. So I know that in this video we talked about a couple of different types of enthalpies, and they might seem fairly abstract. When these are gonna become a value is in the next topic called Hess's law, where we do put these to use.